We're going to, eventually we're moving into statistical inference, and we have most of what we do will be related to either proportions or to means. And it turns out that the probability distribution for proportions and means are different. One of them is a discrete random variable, and the other one is a continuous random variable. And the probability distributions will be a discrete probability distribution or a continuous probability distribution. So one of the things that you're going to do in this section is something that you've done before, and that is to distinguish between variables that are discrete and those that are continuous. A little bit here. Remember that discrete, these are numerical, right? So both numerical. Discrete random variables are random variables whose numerical outcomes are countable, and many times they involve just 0, 1, 2, 3, 4, and you can't have any possible data value that falls between any one of those countable outcomes. So number of siblings is one that I've used in the past. You can have 1 sibling or 2 siblings, 0 siblings, but you can't have 1.5. That's a discrete random variable. And the continuous random variable would be one where the outcomes are not countable. They fall along a continuum. So you could put 10 gallons of gas in your car, or you could put 11 gallons of gas in the car, but you could also put any fraction of a gallon between 10 and 11. So you could have 10.735 gallons. The outcome, possible outcomes to the amount of gas that you put in the car would fall along a continuum. This whole section is about the discrete kind, but there is a section where they ask you, and let's just kind of go down to it right here, just to refresh your memory. Let's do number 6. Read part A, the time it takes for a light bulb to burn out, and is that a discrete random variable or a continuous random variable? Put your answer in the chat if you like. Time it takes. Say hours. Sometimes they advertise. Good for 3,000 hours, 200 hours, or whatever. All right, good. Continuous. Time falls along a continuum, and it could last for 2 hours or 3 hours or any time in between that. The weight of a T-bone steak, part B. Weight of a T-bone steak. Continuous or discrete? Isn't the T-bone steak, you know, it does have a bone that kind of looks like this. And then this bigger piece here, this big chunk right there of meat. That one's called the porterhouse. The porterhouse is part of the T-bone steak. Okay, good. Continuous also. Weight is continuous. The steak can weigh 14 ounces or 16 ounces, but it can actually weigh any amount in between. Part C, the number of free throw attempts before the first shot is made. Discrete or continuous? All right, so looks like you guys have a pretty good handling of these. Someone can shoot 1 or 2 or 3 misses in a row, 4 misses in a row, 5 misses in a row, but they can't miss 1.5 or 1 1/3. It definitely is discrete. Countable number of shots, countable number of outcomes. All right, part D, in a random sample of 20 people, the number with type A blood. Type A blood is the second most popular blood after O, because you can have 1 person in that whole group that has type A blood, or 2 people or 3 people, but it's a survey, so you got to count whole numbers. So you can't have 1.5 people with type A blood. All right, so you're going to be doing a little bit of that, and this is something that you've done before. The other thing that's going to come back is you're going to have these rules for a discrete probability distribution. Now, a probability distribution is, you can think of it as a table where you have each, and in this case, because we're dealing with discrete random variables, the possible outcomes will be numbers. So you'll list all the numerical outcomes here, and then the corresponding probabilities of each one of those. And you'll have the number of rows in this table that corresponds with the number of possible outcomes. But we've seen in the past that these two conditions must be true. The sum of all these probabilities must add up to 1, all these, and that every single probability has to be a number between 0 and 1. And this is consistent. So when you're learning probabilities for the first time, sometimes you'll get a formula mixed up and you'll write, 3 over 2 and get 1.5 instead of writing 2 over 3. Well, 3 over 2 cannot be a probability because it's a number larger than 1. You can think of the probability distribution as just being a probability table. A listing of all the possible numerical outcomes with the corresponding probabilities. Okay, so I think we've had some problems like this before. You have 6 examples, and what I'd like you to do is to circle the ones out of the 9 through 13. Circle the ones that are probability distributions. Cross out the ones that are not probability distributions. So to answer the question, just go through each one and ask yourself, is the sum of all the probabilities equal 1? It needs that property, check. And are all of the probabilities listed numbers between 0 and 1? If the table matches both of those conditions, then you can circle it because it's a probability distribution. And since the outcomes are numerical and they're countable, these would be, if they match those two conditions, they would be discrete probability distributions. And then go write in the chat the numbers that are probability distributions, separated by commas by their numbers. So if number 9 and number 11 and number 13 are all probability distributions, just write 9, 11, 13. Okay. 6 answers? All right, there's a pattern. Yeah, so these, if you add them all together, you get 1, and all of them are positive numbers between 0 and 1. Let's see, this is 0.6, 0.65, 0.9. Yep, this sum equals 1, and all of the numbers are between 0 and 1, so that one works. This one you can exclude because of the negative probability there. Even though I think it's probably the case that if you add up all the probabilities, you get 1. .33, 0.55. Yeah, I think the sum is still 1, but it has to match both of those conditions, and it fails the condition where you have a probability that must be between 0 and 1. Doesn't work there. Okay, this one here, yeah. Sum is equal to 1, so that property is good, and all the probabilities are between 0 and 1. So that one there works. And in this one, the sum is equal to 1.25, and in this one, the sum is equal to 0.35, 0.55, 0.95. And because of that, the sum is not right, so therefore not a probability distribution. What's the missing probability? If this is in fact a probability distribution. 0.45, 65. All right, so I think all of this adds up to 0.85. Yeah, so you have to have a number between 0 and 1, and you have to find the number so that when you add up all 6 of these, you get 1. So you know the sum of all those that are there, 0.85, and so you are correct, 0.15. All right, so now we're going to go into the 2 big calculations for today, and it turns out that it's not anything new. It's a formula, kind of the same formula that we used when we were dealing with weighted means back in section 3.3. You have the data values in L1, you have the corresponding weights in L2. The only difference is that the weights here, in this example, will be probabilities. And then the way that you're going to calculate the mean is to use one variable statistics. All right, here is the main calculation for today. We can do this one by hand. It's not too complicated, but usually we're going to use the calculator for this. And it's called the mean of the entire probability distribution. And what that translates into is the expected value. So when we interpret the mean of a discrete random variable, it's going to be the expected value. So the way that we would write the mean of a discrete random variable, x is equal to the discrete random variable. Then mu of x means the mean of that variable x. And what they're saying is that that's the same thing as the e of x. And the e of x is what we're going to be calling the expected value. So the expected value is, think of it this way. If you had a probability distribution that looked like this, and maybe it was just, could be a dice example with the numbers 0 through 5 on it. It could be a spinner where you're spinning and you're landing on a 0, 1, 2, 3. The question is, in the long term, if you've spun this spinner or rolled this die, billions and billions of times, what would be the average roll if these probabilities hold? They're not equally likely, as you can see, because 0 is going to occur more often than say the 5. But with these probabilities, what would you expect the roll to be? Or what would be the long-term average of all those numbers? So the expected value calculation is going to look like this. We're going to add another column, and we're going to multiply the x value times the corresponding probability. Then we're going to sum all these together. So the sum, we're going to take each x and multiply it by its probability, and then sum up all of those products. And that's what this formula down here says. You see the x times p of x, and then the summation of all of those. All right, we'll get into calculating a couple in just a second. The other thing, the probability comes into play here as well when we do the standard deviation, but we're not going to use this formula. If you ask for help in this section, on My Math Lab, it's going to take you through a table approach, this big table. What we're after on the calculator is sigma. That's the standard deviation. We've always known it as a standard deviation. This one, in earlier contexts, we've referred to it as the population standard deviation. And you'll even notice that the Sx that appears first is going to be blank. The calculator will recognize that you're in a context where you're not taking a random sample and doing a sample standard deviation. You have the entire probability model, the entire probability distribution. All right, well, that's it in terms of, the formulas. Now let's look at some problems. I will walk you through the calculator steps, but if you don't have those, here it is. It's basically, we're going to take the X values and put them into L1. And then we're going to take the probability values and put them into L2. And then we're going to run one variable statistics. You want your X list to be L1 and your frequency list to be L2. But the frequency list is going to contain the probabilities. In our earlier context, the frequency list was a list of whole numbers, frequencies. Okay, let's take a look at some examples. This one, I might just go ahead and calculate it by hand, but we're eventually going to use the calculator. So this is marriages. In the following probability distribution, the random variable X represents the number of marriages: 0 marriages, 1 marriage, 2 marriage, 3 marriage, 4 marriage, 5 marriages. 5 is the largest we have. Elizabeth Taylor. Of marriages an individual age 15 years or older has been involved in. Okay, so 0 means that they've had 0 marriages. So these are the single people. Over 1/4 of all adults 15 years and over have never been married. 0 marriages. Over half, close to 60% of marriages have just a single marriage. So people have been married exactly once. No divorces, I guess. Then there are the folks that get divorced. So single people, people who don't get divorced, and all of these folks have been divorced, presumably, at one point. 2 marriages, 3 marriages, 4 marriages, 5 marriages with the corresponding probability. So it's 1 in 1,000, 1 in 1,000 people in the United States 15 years and older have had 5 marriages. This is 4 in 1,000. This is 1 in 250 people have had 4 marriages. Okay, the first thing is just to understand. And the question that we're going to ask in this section is, okay, if we randomly selected someone, how many marriages would we expect them to have? So, first of all, we'll calculate the expected value. And our author abbreviates it E of X. Calculate this next column here, and we're going to multiply. 0 times 0.272, that one's easy, and 1 times 0.575. Just multiply the numbers together. And then 2 times 0.121. And then 3 times 0.027. And then 4 times 0.004. And then 5 times 0.001. And then we're going to sum up all of those numbers. 0 plus 0.575 plus 0.242 plus 0.081 plus 0.016 plus 0.005. And if you add them all together, that's the expected value. Now, just like the mean is not always a nice whole number when we're expecting a whole number, you'll find in this case that the same thing applies. Okay, so we're going to say that we would expect, on average, in the long run, we randomly select somebody from the United States, 15 years of age or older, we would expect that they would have 0.919 marriages, so close to 1 marriage. All right, now let's go ahead and use the calculator approach. And with the calculator approach, we're not only going to calculate the mean, the calculation we just did by hand, but we're also going to calculate the standard deviation of the distribution. And, if you look at the possible outcomes, if this was bell-shaped, from 5 to 0 would be 5, divided by 4, 1.25. But the probabilities are different, and this is skewed to the ones, to the lower side, so skewed to the high numbers, skewed right, this probability distribution. So we're going to go to Stat, and then Edit, clear out the lists that are there, and then enter all of our possible outcomes, 0 through 5. And then write down the corresponding probabilities. And this is new because normally, I think we did a little bit of this when we were doing weighted means, but for the most part, if we had a frequency list, we actually put whole numbers in here. Now we're putting probabilities. So we have the entire probability distribution in our two lists. Now from there, we're going to do one variable statistics. So I'm going to, I don't know what this is. So I'm going to go to one variable statistics, calculate, just as we did in chapter 3. And remember, you want the L1 to be the X list and the frequency list to be L2, and then calculate. And the first number that you're going to see, the X bar, that is the expected value. Now it's not going to write E of X there, right? Because it always writes X bar. But you need to know that X bar is the mean, which is the expected value. So that's going to be the main calculation. We can do it by hand, we can do it by calculator. The number that the calculator would give us, that shows us the advantage of the calculator, is the standard deviation here. Notice that the sample standard deviation is blank. The calculator doesn't know what to do with a sample standard deviation when you're giving it a mathematical model of probability distribution. So it doesn't calculate that one, but it does give you the standard deviation of the probability distribution. And then you can round that as you need to. All right, that's kind of all preliminary stuff. You know, whenever you see a probability distribution, you're almost certainly going to be asked for the expected value in the standard deviation. So it's always a good idea just to put these numbers in L1 and L2 and do this calculation. You can actually see that a couple of the questions here, they actually ask you, compute and interpret the mean, 0.919. We would expect a randomly selected person and again, we have to be sure that we're clear about the person. You know, what persons are we talking about? Well, 15 years of age or older. To have about 0.919 marriages. Here's how you interpret the expected value. If X represents the number of marriages, then the expected value of X means the expected number of marriages. So the expected value is linked to that X value there. These are the possible X values. This calculation is what we would expect, kind of like the long-term average. The standard deviation, it's about 0.739. We did that calculation. We didn't do A, I think maybe we did A. The sum of these probabilities, now when you're rounding them, not these, the sum is equal to 1, these. You can add all these together and you'll see that they equal 1. And all of these probabilities are numbers between 0 and 1. So just like we did in the earlier example, they want you to confirm that this is in fact a discrete probability distribution. Okay, whole numbers, or at least a countable number, all numerical. Now the graph, you can graph a probability distribution, and you can graph it just like a histogram. So let me do that here. So I'll label that axis probability, And then over here we have our 0, 1, 2, 3, 4, and 5, all 6 of our outcomes. And then just draw a bar that's equal to the probability here. So for 0, we have a probability of 0.272. So 0.272 would go up to about right there. This is a histogram, so these bars should be connected. For 1, we go all the way up to 0.575. And so on. 0.121 and 0.027 and 0.004, and they get pretty small. So this is definitely a right-skewed graph. So where it says in part B, draw the graph of the probability distribution, just graph all of your x's, which is marriages, and then the probabilities. So you're basically graphing these as you would a histogram. All right, so we've confirmed that this is a discrete probability distribution. We've drawn the graph. Part B is here. We've calculated the mean and the standard deviation. And then the other thing you're going to be asked to do is to calculate some probabilities. So E and F, probabilities. The nice thing is that all you have to do to calculate these probabilities is to interpret this table. Because all the probabilities, there's only 6 different outcomes. Therefore, there's only 6 different corresponding probabilities. So this says, part E, what is the probability that a randomly selected individual 15 years or older was involved in 2 marriages? Now I will interpret that to mean exactly 2. Because, you know, these folks here had 2 marriages also. They just had an additional 2. So, yeah, and then you just kind of look, because this table gives you each outcome and the corresponding probability. So when it says, what's the probability that someone would have exactly 2 marriages, you just read the table. 0.121, there it is. And what's the probability that a randomly selected individual was involved in? Here's at least 2 marriages, at least 2. So when you look at all of our possible outcomes, at least 2 means 2 or 3 or 4 or 5. So then you'd have to count up all the probabilities, or just add up all these probabilities corresponding to 2, 3, 4, and 5. So add up those 4 numbers. What's that, 5.3? 1.153? All right, I want to show you something here. This is not quite a probability distribution because we have the frequency here. So they tell us that there are 900. So if you added up all those numbers, you get 900. But these numbers are not probabilities, and so therefore we do not have a probability distribution. What you'd really have to do here is to add another column that gives you the probability. All right, so this is the ideal number of children to have in a family. So they asked 900 adults and said, what's the ideal number of children that you'd have in a family? And you had 10 people would say No children, no thanks. The most popular response of all of these was the 520 out of these 900 said the ideal number of children in a family would be 2. This has changed over time. In earlier times, this number would be much higher. Okay, so this is the same idea. This is a relative frequency. So it's the same idea of problems that we've done in the past. So if you do get a frequency table, you need to convert it to relative frequencies because relative frequencies are the same thing as probabilities in this context. And, you know, get your calculator out and change these into decimals. Decimals are more meaningful in this context than are these rounded, or these fractions, reduced or otherwise. All right, well, this one is about 0.011, this one's about 0.033, this one is about 0.578, and so on. But there you can see, all of these probabilities are between 0 and 1. I assume with this problem, it was one where they asked you to calculate the expected value. So let me show you a couple of calculations here. The first one is we're going to put all of the outcomes, 0, 1, 2, 3, 4, 5, and I think we just need to add the 6 here. Oops, so we don't have 0 through 6, so there's 7 of them. Oh, there's 0. Okay, so 0.011, I'm going to write the decimal versions. And with the probability distribution in there, we're going to do the same calculation as before. One variable statistics, L1, L2, and we get 2.448. Notice the standard deviation is left blank, and it does report the standard deviation. So we would say the expected value is equal to X bar on the calculator, which is 2.448. So we would expect, on average, that if we randomly selected a person, that they would say that the ideal number of children to have would be 2.448 children. And the standard deviation is 0.8278, we'll call it. Those are the two numbers you're most likely to be asked to calculate. And if you're not given the probabilities, you have to calculate them. Let me just show you another calculation. And so you know what these numbers are. I'm just going to go back to the stat menu, and I'm going to change these L2 values to the actual frequencies that appeared in the problem. And I'm going to redo the calculation just so you can see what's going to be similar and what's going to be different. So now we have the frequencies. So both of these columns now are in there. If you run one variable statistics again, and I'm not sure why it didn't give us the, oh, did it? Yeah. It's close, and the reason why it's not exactly the same is because when I put these numbers in, they were all rounded. So there's some rounding error going on here. If you compare 2.448 to 2.4477777. This is the actual mean. This is an approximation. But even this one would round to the same thing. And if you look at the standard deviation, 0.830 something. It's going to be a little different because the first time I did it, I rounded these percentages. And that's why it's not perfect. Okay, calculating the expected value. Let's take a look at an application. Number 26. It's nice when you have the tables and they give them to you. The easiest ones where they give you a list of all the outcomes and the corresponding probability. Here, they almost gave you the whole table. They gave you the number of the outcomes, and then you had to calculate the probabilities. And then there's going to be this whole group of problems where they just give you a word problem, and you have to calculate the expected value. Compute and interpret the expected value in this context. So you have to come up with the table. So you want some numerical x, and you want the corresponding probability. Now this one here is a life insurance policy, and so the way that a life insurance policy works, it's called term life. This one, there's whole life policies. This one's a term life policy. And what that means is that, you know, someone buys a policy. In this case, the policy costs $350. And this is a charge that if you want life insurance, you'd have to pay it every year. And usually when you get older, they jack up the price. So this year it might be $350, next year $360, $370, and it continues to go up. And the way life insurance policy works is that you have two different outcomes. The insured person, they either survive the year, that is, they don't die, or the insured person dies. When you're an insurance company collecting $350 for every policy that's purchased, you know, that $350 can add up quickly. But if the person happens to die, this is a 20-year-old male. If the 20-year-old male dies in that year where they're insured, then the insurance company has to cut a check for $250,000 to the family of the male who died. That's how it works. So you either get $250,000, but you probably don't want the $250 because that means you're dead, or you just pay it. So it says determine the expected value to the insurance company. So we're going to let X be the profit to the insurance company. Someone buys a policy. Well, we don't know whether the person is going to survive the year or whether they're going to die. So in terms of the insurance company is going to take in $350 no matter whether the person dies or survives the year. In an insurance policy like this, if someone were to die, they would cut the check for $250,000. They wouldn't give the $350 back. They keep the $350. All right, so let's fill in the rest of this table. I think we have all the possible outcomes that can occur. So it's kind of like it's like this table here, but instead of having 1, 2, 3, 4, 5, 6 outcomes, there's just 2, survive and die. So it's a much smaller table. All right, let's continue with this. We're not quite done. If the person survives a year, that is, they don't die, then the insurance company has to pay out nothing. If the person survives, they keep the $350. If the person wants to buy some more life insurance in the next year, then they'd have to fork over another $350. So The net profit to the insurance company if the person survives the year is $350. Now, on the other hand, let's say somebody buys, this 20-year-old male buys an insurance policy for $350, and then that person dies in the year. Well, the insurance company, they have to pay out the $250,000. Now, just to give you kind of a context here, when my kids were born, I'm married, and I had a $250,000 life insurance policy. And the idea was that if I died, which was very unlikely, even if you're 95 years old, you're more likely than not to be around next year than not. In fact, the probability is probably higher than 80%. At any age, if you're alive, there's a very high chance that you're going to be alive in the next year. I purchased a $250,000 life insurance policy for my family, because I have 2 kids, thinking that if I were to die, I would like that $250,000 to be available so that they could have their colleges paid for and for some other things. And so I was willing to fork over that $350, $400, $500, and it grew over years. And so as soon as my kids got through college and they didn't need that money for college anymore, I stopped with the life insurance. I just stopped paying the $500 a month or a year. And because I no longer needed it. So it might seem like a lot of money, $500 a year, to pay for something that really gives you no value. And the only time it does give you value is when you die. It doesn't sound like a very good investment, but it's insurance, right? Insurance companies are there to make money, and they do serve a purpose. And if you die, they will pay you. Okay, now the probabilities you're going to get from up here. So it says that the probability that a 25-year-old male would survive the year, it's very likely, 0.998. So that's if the person survives, 0.998734. They just give you that one probability. Now you have to deduce this other one because, and you can do it because there's only one other outcome. And you know that the sum of the outcomes must add up to 1. So if this one's 0.998734, this is the complement, 0.001266. So there's the table. It takes a lot of work to figure it out, what goes where, but you've got all the possible values. I guess I didn't write this one. What's this one? This one's negative 249,650. All right, so you take the 350 and subtract $250,000. And it's negative. All right. You can punch this into your calculator and do one variable statistics, L1, L2 if you want, but this one is so short that I'm just going to do it by hand. We have to multiply 350 by the 0.998734, and then we have to multiply the negative 249,650 by 0.001266. So we're taking the number in the X column and multiplying it by the number in the probability column. And then the expected value is the sum. So we're going to take 350 and multiply that by 0.998734, and then 249,650 times 0.001266. Now, we know this number has to be less than $350 because that's all they take in per policy. But over time, they're going to pay out $250,000 every now and then, and that's going to shrink, reduce their profit of $350. So this number has to be less than $350. It can't make more than that if all they charge is $350, and once in a while they have to pay out $250,000. But here it is. So we would write it in context. 33.5, this is a dollar amount, so we get this. And so what we can say is the insurance company can expect to make. This is the expected value. And expect to profit by $33.50 for each policy sold. And that would be the interpretation that they ask for. Compute and interpret. So here's the interpretation. Okay, one last problem. Why don't you go ahead and do it and just do C, D, E, and F. Just do these here. At noon every day, the manager goes out and counts the number of cars waiting in line for fast food at Wendy's, and does it for many, many days, and then writes up this probability distribution. So it turns out that at noon, that there are 6 cars waiting in line at noon 13.2% of the time, or the probability is 0.132. The largest probability in this entire list is this one here. So the most popular data value is 4 cars waiting in line at noon, but sometimes there's 12 cars waiting, but that only happens 6 times in 1,000. So if we checked at noon and we counted the number of cars waiting in the drive-through, the question is, in this section, how many cars would we expect to see? Or what's the average number of cars? So you can kind of use the same intuition as you have, low on the outsides, and the probabilities get higher in the middle. So this is probably bell-shaped. And if it's bell-shaped, the mean, which is now the expected value, would be somewhere in the middle. So I'm thinking somewhere along, right in the 5-car range, 4 or 5-car range in there. Now, they did write this table in 4 columns, but that was only to save space. You're going to put all of the X values going from 0 to 12 in L1. And then you're going to match those 13 values with their corresponding probabilities in L2. So it's a continuation. You're not going to use 4 lists here. So expected value, I'm guessing, is about 5, and the standard deviation, I'm guessing to be about, again, bell-shaped. So from 0 to 12, that's 12. Divide by 4, it's about 3. All right, it might be lower than that. If we divide 12 by 6, it's going to be 2. So I don't know, somewhere between 2 and 3, maybe. Like there's a higher chance that there's 12 cars waiting in line than there are 11. Interesting. There it is. Did you get 4.87? Okay. And then there's the standard deviation, 2.2. And so the mean is the mean of the X, all this notation, 4.87. So in the long run, we would expect on average there to be about 4.87 cars waiting in line at lunchtime. Standard deviation, also from the calculator. So those are the 2 harder calculations, and then the probabilities you get just by reading the table. Probability that 8, exactly 8, probability that X is equal to 8, are waiting in line for lunch. There's 8. Write down the probability that's right next to it, right there. And what's the probability part F? That 10 or more. And we only go up to 12, so what's the probability that X equals 10, 11, or 12? 10 or more. So we would take these probabilities and add them together. 0.019 plus 0.004 plus 0.006, 0.029. Would this be unusual? That number is less than 0.05. So it's less than 5% of the time. And that makes it unusual using our rule of thumb. Yes, only happens 2.9% of the time.